Let's have another look at circular motion. So here we have an object moving around a circle, and the center of the circle is at x-coordinate x0, and the y-coordinate of the center is at y0. And let's say that the angular speed of this rotation is, let's call it k. And remember, this is going to come in angle units per time unit. And we'll always use radians for our angle units here. Okay, so what I'd like to do is find a function x of t that tells you the x-coordinate after t time units, and also a y-coordinate function as well that tells you the y-coordinate of this spot moving around the circle after t time units. Okay, well, let's start with the y-coordinate, I guess. After t time units, let's find the angle that, so you can see once the point has moved a little bit up here, now we have this angle that it's making with its starting point. Okay, so we could call that angle theta. And let's find what that angle is. So this is the angle that's moved through after t time units, but our angular speed is k. So, you know, distance is speed times time. So angular distance, which is the angle, is angular speed, that's k, times t. So after some amount of time t, this angle in here is just k times t. But now we have the right triangle that we've been working with all quarter. We have a horizontal distance here, and we have a vertical distance there. Okay, we want the vertical distance since we're working on the y-coordinate. So our y-coordinate function is, well, we have to start at the center of the circle, and the height of the center of the circle is y0, so I'm going to put that way over here. Now we just have to add this yellow length to get to the height of the point on the circle. And the radius of the circle, I guess we need to name the radius of the circle. Let's call it r. And we've seen that when you've rotated through an angle theta, the vertical coordinate, this yellow vertical distance, is just the radius times sine of the angle. And the angle here is k times t. Okay. Now when you do a similar thing for the x-coordinate, of course the only difference is, since you're dealing with an x-coordinate instead of a y-coordinate, you get cosine instead of sine. And you get the initial x-coordinate of the center of the circle instead of the y-coordinate. So you can see that when you have an object moving around a circle at a constant angular speed, the coordinate functions that you get are both sinusoidal, which means we can sort of understand the sinusoidal motion in each direction just based on what we already know. So in circular motion, the radius of the circle is the amplitude. This k value is just the angular speed of the motion around the circle. And this shift at the end, which we called the mean when we were looking at sinusoidal functions, is just the center of the circle, either the x-coordinate of the center or the y-coordinate of the center, depending on which coordinate you're looking at. Okay, so knowing that the coordinates of a point moving around a circle are just described by sinusoidal functions, and knowing these correspondences between the elements of sinusoidal motion and the geometry of the circular motion, this gives us some great shortcuts for writing down functions when you have things moving around a circle. So let's look at an example. So let's find a function that describes the height of the pictured Ferris wheel car, that's this one right here, after t seconds if the wheel makes 3 rotations per minute. So the height is, I guess we could call that y of t, and since it's a coordinate function for circular motion, it's going to be sinusoidal. So we know that y of t is going to be a sinusoidal function, and we know the amplitude is the radius of the circle times sine of, we need the angular speed here, times t, plus the height of the center of the circle. So let's see, looking at the geometry of this situation, it looks like r is, this 50 feet here is the diameter of the circle, so the radius is half of that, so that's 25 feet. Let's see, the bottom of the Ferris wheel is 5 feet off of the ground, and so the center of the Ferris wheel is, I guess this is 1 radius, so that's 25, plus the 5 feet here, so the center of the circle is 25 plus 5, that's 30 feet off the center of the ground, or off the ground. And now we need to figure out the angular speed of this. Well, actually, we're told the angular speed, it's right here, 3 rotations per minute, but there are 2 issues with this angular speed, so 3 rotations per minute. The 2 issues with this is, first of all, we want to be measuring time in seconds, not minutes, and second, we have to be using radians. So we're going to have to convert this angle stated in rotations into an angle stated in radians. So let's do the angle unit first. So we want to get rid of rotations and produce radians, and 1 rotation is 2 pi radians. Okay, that'll take care of our angle unit. And now we need to convert from minutes to seconds. So we want to get rid of minutes and produce seconds. And 60 seconds is 1 minute. And that will make our angle, or our time unit, what we want. So it looks like in the numerator we have 6 pi radians. And in the denominator we have 60 seconds. So this is going to be pi over 10 radians per second. Okay, now we know our radius, we know the y-coordinate of the center of the circle, and we know our angular speed in radians per time unit. So now we can write down our function. Y of t, the height of that Ferris wheel car, is going to be the radius, which is 25, times sine of pi over 10t plus the height of the center of the circle, which is 30. And there we go. There's a function that tells us the height of the Ferris wheel car after t seconds. There are 2 assumptions about the situation that are built into this formula. So the first assumption is that the Ferris wheel car actually starts here at the far right-hand point. And we made that assumption when we used sine to describe this sinusoidal function. And the second assumption we made is that this Ferris wheel is rotating counterclockwise. And the way that assumption snuck into this work that we did is because we did not flip our sine function. That means that this function that we wrote down is going to start out at the middle increasing. So if the height of this Ferris wheel car starts out increasing, that means this Ferris wheel must be going counterclockwise instead of clockwise.